All right, I'll go ahead and start office hours. So, like I mentioned at the beginning, I'm going to spend the first 10 minutes or so making a correction to last office hours, which was about the direction of skew. I had added it on the wrong side of the equation, so I want to go over the derivation for it because it's almost certainly going to be on your guys' exam. For the last 50 minutes of office hours, you guys can either ask me questions, or like specific questions, specific problems to do, or conceptual questions to talk about. And if everyone runs out of questions before time, I can start coming up with stuff. Or, like I mentioned, I might have mentioned to some of you all before, I can go over the question I got during my interview, the FSM question. So it just depends on how the time stuff works. So before I do the correction for the skew, did anyone have any particular questions that we wanted to do? Just so that if we don't, I can start coming up with ideas of what I can give you guys.
I have just conceptual questions about asynchronous versus synchronous flip flops.
Okay.
So
All right. Javier, did you have any particular questions here?
It's about muxes. So if we want to do like a bigger mux, let's say 8 or 9,
How would you do it?
yeah, would it just be just increase the amount of two to one mux that we use, or
Pretty
we also
much,
use-
but we
also use
can-
cases as well?
Yeah, there's a bunch of different ways to do it. We can go into that. So yeah, we'll talk about that. Did anyone in Discord have any particular questions they wanted to go over today?
Yeah, I had one.
Okay, cool. So what was your question?
Uh,
I know what it is.
It was just on. So, is everything from assignment 2 all the way up to our last assignment? That's all going to be with like on the test, right? Like it can be on
Yeah,
the
it
test.
can be any of that stuff. Yeah.
Oh, okay. Thank you.
I mean, even just generally, if she's talked about it during lecture, that could be on the test.
Okay.
So just keep that in mind. And then yes, any other questions?
I had a question.
Yep.
Could we possibly go over some timing stuff? If that's all right.
Timing stuff. Yeah, we're going to talk about timing right now in the beginning, about skew specifically, but we can do examples of timing problems as well. So I'll go ahead and I'll start, like I said,
Cool,
I'll
thank
start
you.
with the skew. Yeah, for sure. I'll start with the skew review, and then we'll launch into those questions. So I mentioned last office hours about the orientation of the skew affecting which side you add the skew to for your equation. If it's right skewed, which is to say that the first one receives the clock before the second one, you add it to the left-hand side of the equation. And if it's left skewed, which is to say that you have the second register receives the clock first, it's going to be added to the right-hand side of the equation. I'll go ahead and write that out so you don't have to parse what I said verbally, rather you can see it. So I'll go ahead and write it out on the board. There we go. Okay, cool. So the diagram I've drawn up on the board is a diagram of what happens when your first register receives the clock before the second register does because of some amount of clock skew. So I'm going to call this right biased clock, just because that's kind of the way the buffer's pointing. You probably won't hear that terminology used elsewhere. It's just one that I use for myself. But in general, this is just done when register 1 receives the clock before register 2. And so we can talk about how to analyze the circuit and decide how to modify our timing equations, because we have two timing equations to modify. So we have the clock time equation. That's our first equation we're going to modify, which has to deal with the clock time. And then we have the hold time constraint. And so we're going to take a look at this diagram and figure out what we need to do with skew in this equation, whether we need to add it to the left or to the right. So for this first example, I'm going to, in my mind, pretend both clocks work off just this first one, pretending there's no skew.
The only thing you know how to do is solve the
These three time intervals are going to represent my delays that I have from this equation. So that first time interval I'm going to call TPCQ, the time to get read out of the register 1. That second time I'm going to call TPD, that's the delay through the combinational logic between the registers. And then this final block here is going to represent the setup time, which is how long before the clock edge hits the second one that it has to be steady and stable at that wire. You'll notice that in this diagram, I've drawn it such that we have basically the entire interval completely used up. So we're kind of efficiently using our clock such that the entire thing fits within one clock period. There's no like extra time here. That's not being used up. If there was a little bit of extra time, I would shrink my clock period so that I'm using it all efficiently, and I can run my circuit faster.
Okay, do you want us to go up there? Or
Now, when I have skew, this clock arrives earlier in this orientation, and this clock arrives later. So we start by our logic launching out of this first register at its clock edge. But we don't consider the input of clock edge 2 here, but rather for the one where it's,
I like those.
or rather on this clock edge, because that's the one that 2 sees. 2 does not see this clock edge, but it sees this one.
Robbie Fortune.
And so what you'll notice is if I draw that exact same timing on the second one, while it does match up with the first clock edge, actually there's some extra time here that we could be using up if we shorten the period because of the skew. So the skew here is beneficial to the clock period. So we talked about before what we can do when we say best case or worst case scenario. So there's two ways of thinking about it. The first way I'm thinking about it is, or there's a few ways to think about it. One way is, okay, I want to make this time, this period, as small as possible. Because the smaller my period, or the shorter my period, the faster I can run my circuit. If I want to make this smaller, I need to be able to make the right hand smaller. Because this needs to be bigger than the right hand. So if the right hand's smaller, then this can be smaller as well. Well, here you'll notice we generated extra time that we can squeeze out of our circuit, that we can contract the period with, because of this extra little interval here from the skew. Because there's extra time that we can compress the period with, that's the best case scenario. The worst case scenario would be our timing wouldn't even be met. Here we've generated extra time, whereas if we were in the worst case scenario, like I said, our timing constraints wouldn't be met. So we need to think, what's the best case scenario, which would be making the right-hand side smaller, which would be the same thing as subtracting the skew from the right side. This, in the book, would be written as, instead of like this, it'd be added to the right-hand side. And you can write it either way, it doesn't really matter, because when you actually calculate stuff for your equations, it's the same equation, it doesn't really matter much.
That's funny because like Robert, like that, like it's
So, any questions on how we went from here to this equation?
good for him. It was like $12. I know who he is because we talked about it in Fluids. Because
So we talked about how this skew is beneficial for this top equation. Now we're going to talk about how it's not beneficial for the second equation. And so the way we're going to look at it is we're going to start by saying, okay, well this applies after the second clock edge strikes. That's when this equation is used. So we say, okay, we've just received our second clock edge. So I'll start from So clock edge 2 is just struck. And what we're concerned with is we want to make sure that our hold time constraint is met. So there's a little interval
they're printing stuff all day. If you like figure out how to use them.
after the clock edge hits where our signal still needs to remain steady. There's some time before the clock edge hits and time after the clock edge hits when our signal needs to be steady. The time after is called hold time. What we don't want to happen is for a signal to come out of register 1, run through the combinational logic really quickly, and then get to the second register, before that hold time is finished, because then this wire at the entrance of register 2 has a signal value that's changed. So the value on the wire is changed, and now it's going to read in some garbage value. We don't want that to happen. So let's again talk about what would happen if there was no skew. So no skew, both clock 1 and clock 2 have the same edge. And so what we say is, okay, there's this hold time for our registers, and we want to make sure that this is smaller than the time it takes to get out of the first register through the combination logic.
One thing I respect about Robbie though is he will tell you when he's mad at you. Like, okay.
Okay, so what I've drawn here is I've drawn a T hold time, and then the delay to get out of the first register and go through the combination logic to change that wire at the entrance of the second register.
Okay, sounds good. Gavin's
You'll
action.
notice that these two times added together on my diagram are longer than the hold time, which is good. That means our hold time constraint is met because the hold time is less than the sum of these two. But now let's take a look at what happens if there's skew. The output of this register 1 begins at register 1's clock edge, which is here. But the hold time begins at the second register's clock edge. So instead of being up here, it's down where I've drawn it below. But now you'll notice
What day is it? R440 exams.
this actually changes the value of the wire during the hold time, which is bad. The register's not going to read in the correct value. So what that means is we're now in the worst case scenario for the hold time. And so we have to ask ourselves again, okay, how do we make this harder to be met? Well, if this side is, there's a few ways to think about it. If this side is smaller, then this is harder to meet because then you have to make the hold time constraint, the hold time also smaller. So you can think, okay, we have to subtract the skew on this side. That makes it harder to meet my hold time constraint. Or you can just add it over to the right-hand side, or add it over to the left-hand side.
She's like really, really nice.
And say, okay, well, if this is some fixed value, 50, and we have some hold time, 40, then if we add some amount to the hold time, eventually we're going to exceed this, and so our hold time constraint will be met. So it doesn't matter which way you write it. You can write it as in a plus on the left or minus on the right. Both are the same, and both apply to this case. Now, for the second case, it's exactly the same analysis, except at the end, we're going to come up with the equations as being, well, there's a few ways you can write it. I'm going to write it the other way. TC greater than or equal to TC Q.
Yeah. I just, when I did it with absolute pressure, the answer just seemed wrong. So it's, or using pressure. So it's like,
This is the case for when we have that register 1 receives the clock after register 2.
I was really glad when she did the equation there because I was like, yeah, we did like, yeah, I was assuming that she did. None of the
So everything that we did for this analysis up here would be reversed. And so instead of adding to the left-hand side, we added to the right-hand side. And, no, I missed a turn.
like that one was way easier than the other ones. I just didn't know like what to do. Yeah. But whatever. Okay. I'm gonna go.
And just as a quick reminder, this top one is the best case scenario for the clock time, and the worst case scenario for the skew, or for the hold time. And it's exactly the opposite in the second case. It's the worst case scenario for my clock time, and it's the best case scenario for my hold time. Okay. Now, as maybe like a quick way to remember it, if it's right biased skew, so the first clock receives it before the second clock, you add to the left-hand side. And if it's left biased skew, the second clock receives, or the second register receives before the first one, you add it to the right-hand side. There's a bunch of ways to kind of memorize it, but it's very helpful to know how to derive it, in case your memorization fails. Okay, so I spent a little longer on that than I wanted to, but that's fine. So now that I've kind of talked about skew, does anyone have any questions about this? Alright, so what we'll do now is we'll start going over the problems that everyone wanted to go over. So we want to talk about the multiplexer, we want to talk about timing, and then what was the one you were asking? Asynchronous, synchronous reset. Okay. And then were there any other suggestions from the Discord about things to go over? I think we got one other person, in case you have any particular questions that you want to go over. Okay. So we'll go ahead and start with the asynchronous versus synchronous reset. And you were asking like about the gate level design, or how to like do it in Verilog, or what?
Not Verilog. I was wondering about, first of all, is there a difference? Like, I think I've heard settable flip-flops and resettable flip-flops. Is that something different?
Yeah, those are different, but only very slightly. So,
Where one has like a set
and the other has a
clock and
reset.
the other has a reset
Yeah.
clock.
So all that it means is that if it's a resettable flip-flop, that means that when the reset signal goes on, the value in the register goes to 0.
Oh, it goes to 0, yes.
And then when you have a settable register and set goes on, then the value inside the register goes to 1.
Okay.
You can have a resettable and a settable register, so that it has both those functionalities if you wanted to.
And that's not the same as an SR latch? Because this is like a clock edge. with the flip-flop?
It's not the same as an SR latch.
Okay. Okay.
It's
That
not the
doesn't
same as
have
SR
the
latch.
clock.
Correct.
Okay. Okay, and then my second question was, like, for the synchronous resettable flip-flops,
For synchronous resettable flip-flops, yeah.
do we have any sort of truth tables, like the enable flip-flops, or do we have, like, can we draw a schematic? to see how
We can
that
go over
works?
drawing it, yeah, and we can talk about how to maybe do a truth table.
Yeah, that would be great. 'Cause I think that's what I'm missing.
Okay, so I'll go ahead and draw up on the board a black box diagram of a resettable, or sorry, not a resettable, it was a synchronously resettable.
Synchronously resettable
Like,
flip-flop.
maybe also
Yeah.
working on like ideas and stuff because we'll meet up as leads, and so that's kind of the most that I would like you to do that. Honestly. Well, yeah.
Okay, the black box diagram doesn't really specify synchronous versus asynchronous. That would just be something in the actual schematics and the design that you would specify. And so we can go ahead and open this up. And essentially what we're going to have is just a normal flip-flop.
Yeah, that's kind of sad. If you like, and that's the thing. It's like if you want to kind of be a part of that, then that's fine. But I don't want you guys to like get sidetracked with other stuff when you're supposed to be doing.
And at this input, we're going to have some extra logic to make our reset. And so here's what we're going to do. We're going to make a truth table for it. So at this wire, at this input, we want to read a specific value into the register. So this is, despite the fact that I've labeled it DN, DN is going to be the output of some sort of combination logic here. So in my truth table, that's going on the right-hand side. And on the left-hand side, I have two
And I
signals.
think that you like
I'm going to have D, which is an input to my register,
like just like even just like using tools and shit. Like I
and
think
reset,
like,
which is also an input to my register.
than pretty much all of us. And so like
So
I
here's
think
what I'm
that-
going to do. I'm going to go through every possible case with this truth table, and then we can write out the Boolean equation for it, and then we can draw the schematic from there. So, what happens if reset's on? What are we going to input to the register? Yeah, 0. If reset's on, we want the register to read into a value of 0. And then, does it matter what D is? No. So I could write this as 2 rows if I wanted, and the 2 rows would look like 1, 1, 0, 0, 1, 0. But I'm going to write it as 1 row succinctly. If reset's on, it doesn't matter what D is, and our output's going to be 0. Now, if reset's off, and D is on, what's DN going to be?
Should just get, it's like a regular D flip-flop, so it should get D.
Which in this case
which
is. And we could also write, for this next case, 0. Because here, reset's off, and D is 0, so DN gets 0. Now we can make this even more succinct. We can kind of condense this truth table as follows.
Was it like tools besides like an Allen wrench, like putting fucking IKEA shit together? You know,
If reset is on, dn is 0. And if reset is off, dn is d. This is just another way of writing what I've written on the left. Now, I'm going to go ahead and derive the equation from this truth table and derive the equation from this truth table and see if they're the same. So from this one, when we make an equation from a truth table, we circle all of our rows where the output is 1, and we write down the equation for it. So the output is 1 only if d is 1. So that's going to be part of my equation. So dn is going to be equal to, well, only if d is on and r is off. So that's the equation I've derived from this. And I can do the same thing over here. Maybe more obviously we can see it here that dn is only on, r is off, and d is on. D and r. You'll notice that I actually have the same equation in both cases. This is just a slightly different way of representing it in a truth table compared to this. But it's the same thing. And so now we can actually write our combinational logic here. So this kind of hidden combinational logic block actually looks like this. We have a single AND gate with an inverter at one of the inputs.
So easy.
Pardon?
It's so much easier than in my head I was like, okay, so then with set, we're just going to change the S, and then when it's 1, we get dn equals S and R, or S and D, excuse me. And it's basically like the same, yeah.
Yep, it's almost identical. So we have one column for this. So it happens when S is on, or if D is on and S is on. Now it looks more complicated. It looks like it has one extra gate. But I will say that this equation can be rewritten. It can be shown either via truth tables or Boolean algebra. You can show that this is going to be the same as that. These two are equivalent statements. I can't remember the theorem.
It's the last one on the sheet.
Yeah, I think it's like the simplification theorem or something. I
Yeah.
can't remember the name. But,
What's this again?
pardon?
S? Just settle?
Set.
Oh yeah, I switched
Yeah,
to
set.
settable.
Yeah, if you had a settable flip-flop. Set just means that if set is on, your register is going to read the value 1. Instead of reset, it reads the value 0. That's the only difference. And so you can write the equation for it. And again, it would be almost identical to this, except it would just be an OR gate instead of an AND. And you could even do both at once. So if you did both, for example, there's one extra minor nuance we have to include, and I'll get to that in a second. And the extra nuance is just what we want to do if they're both on. We want one to take precedence over the other, and it doesn't matter. It's up to us as designers. So what do you think? Should we have reset take precedence or set take precedence? Set? Okay. I mean, I can toss a coin if you want.
Wait. I thought it would be the same case with like the SR latch where it would be
Invalid.
unstable if they're both on.
No, because what we're going to be designing is some circuitry outside of the clock, outside of the register. So inside of here we have some SR latches, and remember SR latches are these cross-coupled NOR gates. And so, because specifically, by the way of this, the hardware being linked back to the inputs, or the outputs being linked back to its inputs, when we put in both ones, yeah, we get an error there. But the hardware we're going to be designing for this, it's not going to have anything to do with cross-coupled NOR gates. You'll see what the hardware is going to look like. So let's do an example of, well, let's do this. If they're both off, it's going to be whatever D is. If reset is on by itself, we're going to reset, it's going to go to 0. If set is on by itself, it's going to go to 1. And then here we have the 1 state. We're going to make logic to put whatever we want over here. We're actually making gates to make it however we want. So we could have it automatically go to 0. We could have it automatically go to 1. Heck, we could even say they cancel out and we just read in D anyways. I don't really care. So what do you guys want to go with?
Kind of like the cancel idea.
The cancel idea? I think it's kind of funny. Okay, we'll do that then. Let's do that. So I'll go ahead and analyze this. So we have a few spots where we have to write our our Boolean equation. So we have this one, and that one. So for that first column, Dn is going to be on if S is off, set is off, reset is off, and D is true. I'll do this bottom one as well. Or if set is on, reset is on, and D is true. Or, and then this middle one here, it's going to happen if set is on and reset is off, and that's it. So these are all of our different terms. And the reason why I wrote these two next to each other is because you can actually factor a D out of both of them. Does this look familiar to anyone? This term?
So that's an XNOR
Yep.
inside.
And so then we could draw the gate diagram for this one. And that would, again, just go at the beginning of my register. And so when you're doing synchronous stuff, it happens that you're almost always going to be just putting logic at the beginning of the entrance of the register. When you're doing asynchronous stuff is when you have to actually open it up and mess with the hardware inside of the register.
Okay, so that was my other question. With asynchronous, does our truth table, do we make truth tables? Does that ever change? Or like, do we just open up the wannabe latch? and
So, I mean, the way that you would, so you open it up and you're like, okay, I need to change something.
then- yeah.
If you already know what it is you need to change, then you don't need to make a truth table.
Yeah.
But to find out what it is you need to change, if you don't already know, you do a truth table just like we did here. Because in our heads, we'd be like, okay, I know that I want it to reset. I know that I want it to set. How do I add that additional functionality? Truth table. Same thing as we did there. We're going to go inside the flip-flop, look at one of the wires and say, I want this wire to be able to have this extra functionality. So I pick that wire and I put some extra inputs before it. That's the general way you do it.
And that was what we did on the.
And that's exactly what we did on the homework. Yep.
Okay. Okay, this is perfect.
All right.
Thank you.
Okay, so
That's
now
the answer we got.
we'll go ahead and talk about the 8-to-1 multiplexer or higher.
I do have a very long question here on that. So if you were to assign, let's just say Y to, let's say the first one, it's not minimized or whatever.
Yeah.
Would it compile to a simpler circuit?
Would it compile to make a simpler circuit?
I'm not sure if I used
Well, no, it doesn't matter the terminology. I get what you're saying. It depends on the software. I think that for Model Sim, they don't reduce the logic, but if you're trying to download it to an FPGA or you're trying to upload it to an FPGA, then the Quartus software is gonna reduce your logic so that it uses as few lookup tables as possible. So it just depends.
Thanks.
Yep. Okay. So yeah, onto the multiplexers. I'm going to go and erase the stuff on the screen, or on the whiteboard. Okay. All right. So now we can talk about the multiplexer. So we mentioned before in the previous office hours how to make a 4-to-1 multiplexer. structurally, which is to say made from other 2 to 1s. So I'll go ahead and redraw that up on the board. And basically the way it works is like this. So you have A, B, C, and D, and we want to pass one and only one of those signals to Y. So we have to pick a select line, 2 bits of select line, S0 and S1, to specify where we want it. S0 is going to specify, well, I'll do it S1. S bit 1 is going to specify whether or not we take stuff from the top half or from the bottom half. If S bit 1 is 0, it's going to read in whatever comes out of this multiplexer. And if S bit 1 is 1, it's going to read whatever comes out from this one. So let's just say it was 0. If S1 is 0, we're going to read in whatever came out from this multiplexer. And then we look at S bit 0. S bit 0 is going to specify whether we do the top or the bottom. So either A or B. And so there's 4 possible combinations for S1 to 0. Each of these 4 combinations corresponds to encoding either A, B, C, or D. Now, if we needed an 8 to 1 multiplexer, how many select line bits do you think we'd need?
3.
Yeah, 3. And we'll have 8 possible encodings, so we'll be able to pick between 8 possible inputs. And I'll go ahead and write up that multiplexer on the board now. And it's going to be deceptively easy how to add on that extra hardware. So I'm basically just going to take another one of these, this entire diagram, over down here. And this accomplishes exactly what we said. So we can look at S bit 0 to specify whether we want to look at the top half or at the bottom half. Let's assume it's 0. That means it's going to read this wire and output it to Y. So now we go up here. S1 is going to tell us whether to read from this multiplexer on here or that one up there. Let's say it's 1. Well, now we look at this guy and we say, okay, S bit 2 tells us to read from D or C, and let's say we just did D. And we can trace back our path. So we have D is 1, we chose 1 here, and we chose 0 there. And so if we choose this as our select line, that encodes D. And that's kind of that's the way that you would make an 8 to 1 multiplexer with a bunch of 2 to 1s.
So conceptual question: are all muxes 2 to 1, or they can be any size that you want?
So 2 to 1, I'm just doing this because we're trying to do structural modules, but you can make a 4 to 1 just at a gate level. So if we wanted to make a 4 to 1 multiplexer, you'd look at a truth table, get the truth table, put it into gates, and then write those gates out. So we can do that. It would be something like this. Well, actually, I'll do it the easier way. So say we wanted to make a 4 to 1 mux. Well, our select line again has 4 possible options. And then our output Y is going to be either A, B, C, or D, depending on which case we're in. And so all we would do is what we would do is we would write the equations corresponding to these. So Y is going to be on if you're in the top case, S1 off, S0 off, and A is true. Or if S1 is off, S0 is on, and B is true. Or, and then we keep going. S1, S0 bar, and C. Or, and then for the last one, it's going to be S1, S0, and D. And so now you'll notice that we have exactly what we wanted. All we have is we have 4 3-input gates, and 4 3-input AND gates, and a single 4-input OR gate that connects all these together. It looks like this. And each of these AND gates is going to correspond to one of these terms. So instead of doing it structurally, where it was just this is a 4 to 1 mux, we now have it at a gate level design. And this is going to look different than that one if we were to open it up and look at the gates, because there's always multiple ways to implement a function. You can always do it multiple different ways. Yes.
Okay. So going back to our original 4 to 1.
This one's a picture of 8 to 1, but
Yes.
this is 4 to 1. Yeah.
Yeah. So wouldn't C be 0, 1? Right? And D is 1, 1. If it's like S.
Oh, you mean like why is this disagreeing with the way I
Yeah.
have it there? Just because it doesn't matter which one you pick as wedge.
Oh, okay. 'Cause I
As long
thought-
as you know, as long as you're consistent. I obviously was inconsistent because I didn't pay attention.
Oh,
but,
okay.
But yeah, so here I would encode 0, 0 as A, 1, 0 as B,
Okay.
and then 0, 1 as C. So
Okay.
all that means is I would switch those two.
So then my second question is, once we do the 8 to 1, like, what would we encode for? Wait, I lost my question.
No, you're good.
Like, oh, okay, so if we like encoded it like 0, 0, 1, that would be E. Well,
So yeah, 0 would correspond, well, I'll start from this end. 1 means the bottom branch.
Yeah.
This 0 means
Okay.
from here the top, and then that 0 means the top one. So-
Okay, yes, okay,
Yep.
just making sure, thank you.
Now again, like I mentioned, if you were to take this 4 to 1 mux and open up the logic in here would look different from that logic there. Doesn't matter because they're both implemented the same way. It's just a matter of whether or not you want modularity in your design or possibly more simplified gates, less gates. So it just depends on your constraints. Because I believe if you do it this way, you'll have less gates in total versus if you do it this way. Okay, so any other questions about the multiplexers? Okay, cool. So then there was a question in the Discord. What was the question again? It was about, well, there was one about timing. We can do timing problems. And what was the first one about? So I can't remember off the top of my head.
Wait, was it like my question?
Yes.
Oh, no, you already answered it.
Did I? Oh,
yeah,
no,
'cause
that's
I-
right, because it was just asking.
Yeah.
About, yeah.
Yeah.
There was one question for someone who left earlier about doing timing analysis, which we kind of did at the beginning. Are there any other questions anyone has for me?
Nothing top of my head.
Okay.
We didn't do any JK flip-flops yet, right?
No, I mean,
Uh,
I don't think you've done any, have you?
We did that in
No, I don't think so.
Okay. Yeah, I mean, it's just another form of a flip-flop. Do you guys know why JK flip-flops are even a thing? Because it feels weird. It's like you have 2 inputs that's more complex, and you can just accomplish the same thing with a D flip-flop if you just add extra logic to the beginning to make it toggleable or resettable or settable. Feels weird. Does anyone know why JK flip-flops are a thing? If you break it down to the transistor level, they actually are more efficient than making a D flip-flop and then putting extra logic at the beginning. So it uses less transistors, less hardware, and you get all the functionality that you could get with a D flip-flop and more, which is you can toggle, you can set or reset. So that's the main reason why. And I can't remember who made it. I know their initials are J and K because it's the JK flip-flop, but I can't remember who made it. And that's the reason why it's a useful one. Let me see. There we go.
Further questions in the public area?
No. No. But she did mention, like, oh, I could ask her about boxes or decoders.
Oh.
Decoders are the easy one, though, because it has, like, all the inputs are, like, 3, 0, 1, 2. But there's no, like, set label, right? Isn't it just, like, the inputs equal the outputs? Or, like, you have 8 inputs and you have 8
Can we go over them?
Yeah, I think we should.
Yeah, it's basically like a fancy truth table. That's what you can think of as a decoder as. So there are a bunch of like different decoders you can talk about. One example of a decoder would be a 3 to 8 decoder as follows. So we have a 3 to 8 decoder here, and I'm going to make this a 1 hot decoder, or I guess you would maybe call it an encoder because you're changing it from binary to 1 hot, just like that. So I'm going to say the purpose of this is to turn a binary number into an equivalent 1 hot representation. And that's what my decoder is going to do. And so all that's going to happen is, if I were to look at a truth table, the first case where you have all zeros at the inputs, I'm going to say is corresponding to this. So when I plug this into the decoder, my decoder is going to spit out this. When I plug this into my decoder, it's going to spit out this, and so on. And you continue, and you'd have the rest of the ones. This is just a particular example of a decoder with a specific purpose. So there's a bunch of different ways to implement this. This could be implemented as a memory unit. So if you have a unit of memory, DRAM or whatever, these will be the address bits. So you say, you know, this will specify which particular index in your memory you're going to be accessing, and then at each index in that memory is this value, or that value, or that value. And the output is just reading from the memory. So you can implement a decoder as a unit of memory. Otherwise, you can also do it as like a lookup table. That's just another word for memory in this case. Or you could implement it at a gate level design. It doesn't matter which way you do it, they both accomplish the same thing, which is you receive a set of inputs and then you have some sort of rule to say, with these inputs, there's an output. So, like I mentioned, it's just a fancy truth table. That's it.
It sounded it was actually.
Okay. Any other questions in regard to that? Okay, and then, oh yeah, AJ, in Discord, you had a question about timing analysis stuff. Did you want to go over a timing analysis problem? I don't know if I can hear you. You can also type in the chat. You can't use your mic. Okay. Well, I think I'll just do a timing analysis problem anyways. and then from there, we'll see if anyone else has any other questions. So I'll go ahead and erase this from the board. So, for a timing analysis problem, typically what you'd be given is you'd be given a circuit with a bunch of values, numerical values, which would correspond to just something you'd see like on a data sheet for, say, a register or for logic gates. And you'll be given a register on the left, a register on the right, combinational logic leading between them, and then, like I mentioned, like a setup time, a hold time for the registers, delay for gates, and then a skew of the clock if there's a skew in the problem. And likely what's going to happen on your test is she's going to give you, almost exactly like the homework, she's going to give you a problem with no skew, and then she's going to give you the exact same problem and ask you, okay, same circuit, same problem, how much skew can it work with? That's likely what it's going to be. So what I'm going to do is I'm going to do the following. I'm going to draw up a circuit on the board.
Sorry, I just got back. Are we still going over timing problems, or is it something new?
Well, we went over a few other topics while you were gone, but we're now just starting a timing problem example. So you came back in time.
Okay, cool. Thank you.
Yep. Right now I've drawn in the buffer here to suggest that there's clock skew, but I've written 0 picoseconds just to say, for the moment, let's consider no clock skew. So what I have here is a 3-bit register outputting to a bunch of combinational logic gates, which inputs to a 2-bit register over here. And so we need to do some timing analysis, so I'm going to select some values for hold, setup, and stuff like that. So I have a few values for my setup, my hold, and then the range for being read out of the register. And I'm also going to write down that, well, I don't know if you guys have had an example like this, but let's do different gate delays for the different gates. So I'll say the delay of an OR is going to be, let's do 100 picoseconds. Well, let's do it like this. You're given just a huge list of values, and you're basically asked, okay, we need to figure out what the maximum operating frequency for the circuit is.
Oh, we do have
Or
the sorry.
and inverter. Sorry. No, you're good. I just want to make sure I have them all. So we want to find the maximum frequency the circuit can operate at. So I'm not going to start it. I want you guys to tell me what to do first. It's the very first thing we should do. What do you got?
So I would say what we learned in class is probably the first thing we should do is make sure that we are in the hold constraint zone, because if we're not, then we're just done.
Yeah, exactly. I'm pretty sure I made the numbers so it works, but we should still check. Because if I made the numbers so that it doesn't work, it would be kind of a bad example. Okay, so let's go ahead and check our hold time. So our hold time equation is going to be as follows. Now, this is without skew, but let's consider what each of these terms are going to be. So T hold, that's given to us in the problem description, that's 15 picoseconds. TCCQ, that's the smallest or the shortest time that you can go to be read from clock to Q for your input register, or for your first register, which I've written as 7 picoseconds. And then TCD, that's just the contamination delay through the combinational part of our circuitry. And so we basically have to ask ourselves, what's the quickest path through? So does anyone here know what the quickest path through our logic is going to be?
It would just be the C, right?
Yeah, it'd be C through the OR gate to Y0. So that delay there is 70 picoseconds at a minimum. And so we actually get that our hold time constraint is very easily met, because on the right-hand side we have 77, and on the left we have 15. If I didn't want there to be a hold time constraint being met, I could instead change the circuit to be like this. So we have another registered input, but here the delay is none. And so we'd have 7 picoseconds plus 0, and so our hold time constraint would be violated, and our answer to this problem would be it doesn't work. However, just so that we can continue with calculations, I'm going to assume that's not the case.
Yeah, she did say she might give us one that just doesn't work.
That is a possibility.
Just gonna play with it.
Yeah, one more.
Yes. So just keep in mind, if it doesn't work, you can just say it does not operate reliably at any frequency. Or just say it doesn't work. I think she'll be fine with either. Okay, so now we want to figure out what our frequency is. And to do that, how are we going to get our frequency? What do we need to find? Or what equation do we need to use?
Forgetting the equation.
It's all good. What's the name of the equation?
Clock time.
Yeah, I mean, there's the clock time is the term in it. But I think traditionally it's called the setup time equation. So this is the hold time, and the other one's the setup time. But you can call it whatever you want.
Cycle time.
Cycle time. I like to call it the cycle time equation. Yeah. So we have that the cycle time, or the clock time, is going to be the longest delay to go from the clock to our outputs, plus the longest delay through all of our combinational logic, plus the time we have to spend waiting at the entrance to the second register, holding steady. Which again is called the setup time. Okay, so what's TPCQ here?
Uh, 20?
Yeah, I wrote that as 20 picoseconds. I'll do the easy one for you guys. T setup is going to be 40 picoseconds according to what I've written. And I'll let you guys think about the hard one, TPD. What would be the longest delay through our circuit?
That's inverted, right? A is inverted first.
Yeah, so A is sent through an inverter, then an AND gate, and then out one of two ways. That's right.
Yeah. Okay.
Any suggestions for the longest path?
I believe it should be A to the inverter to the AND gate, then the XOR, not the OR gate, right?
I think that's correct, yeah. So definitely we're going to hit quite a few gates if we travel on A through the inverter through the AND. And then we can pick either the XOR or the OR. XOR has longer delay, so we go through the XOR. Inverter has a maximum delay of 40. The AND gate has a maximum delay of 110, so 40 plus 110 is 150. And then the XOR gate has a maximum delay of 150, so 150 plus 150 is 300. Okay, everyone get 300, just to double check my math. Okay, so we can add up the right-hand side, we get 360 picoseconds. And so the smallest clock period we can manage is 360 picoseconds. And to go from here to the maximum operating frequency, what do we do? Yeah, the reciprocal, because period and frequency are just inverses of one another. Now, if you went ahead and plugged that in on your calculator, you should get around, would it be like 2.8 gigahertz, I think? What'd you get?
2.1.
Actually? Nice. Yeah, so 2.7, no, it was a guess. So 2.78 gigahertz about. And that's the maximum operating frequency. So you would say, okay, hold time constraint met, maximum operating frequency for the circuit without skew, 2.78 gigahertz. Okay, so any questions on that? Okay. So now we can talk about what happens if we introduce skew, and I'll introduce skew in the orientation dictated up there. Let's do a lot. Actually. Now we're asked, okay, we have some skew right biased, so the clock here receives it before that clock, before that register. And so what we're asked is, what's the most skew we can deal with before our circuit breaks, before it doesn't work anymore? So when it's right biased like this, what do we do to our equations?
Can we just say that on the test, or does she expect us to like draw?
I don't know. You can ask her.
Okay.
It will probably say in the instructions if she wants you to do that.
So I don't know if that's like pulling it out of our or
Yeah.
like thin air
I
stuff.
think, if I recall correctly, I think that she might just have part of the problem as derived, kind of like,
Okay.
why do you add it to the left or the right?
Okay.
She might have like a separate part of the problem, or you could just ask her if she wants you to show why you add it to the left or the right.
Sounds good.
But like we've mentioned before, we're going to add it to the left. If it was biased to the left, which is to say this receives the clock before this guy, then we would add it to the right-hand side of both equations. And so now we need to ask, okay, well, if it's in this orientation, what value of skew can we deal with before either of our equations break? And which one is the one that's going to break first? I think it's going to be the t-hold, yeah. Because if you keep adding skew over here, you can subtract it from the right-hand side, and that just makes your clock time shorter. So it doesn't really matter too much. Whereas over here, if you're adding some amount of skew on the left-hand side, eventually the left-hand side is going to not be less than the right-hand side, and our hold time constraint won't be met. And now we need to figure out what value that occurs at. So what did you guys get for the value of the most skew we can deal with before our circuit starts to have a hold time violation?
Is it 62?
I got 62 as well, yep. If you go ahead and subtract the 15 picoseconds over from the right-hand side, we get 77 minus 15, that's 62. And so our skew has to be less than or equal to 62 picoseconds. So at any point greater than 62 picoseconds, we have a hold time violation. And now we can ask another question for if it's left biased. And I'll give you guys a very specific amount of skew. Because if it's left biased, you can always just make your period longer and you'll still have it work. The hold time constraint will be met no matter what, because it's the best case scenario for the hold time if you have it skewed to the left. But you can just keep extending your period. So I'll just give you guys an actual value of the clock skew. And we'll call it 30 picoseconds of skew. And we'll say that that's going to be biased now to the left. Will our hold time constraint still be met? If we have 30 seconds of skew to the left? What do you guys think? If we have 30 picoseconds of skew.
Yes, right,
will.
because it adds to the right side.
Yeah, it adds it to the right side. So the right side would be 117 and the left would be 15. But even if it was biased the other way, it would still be within our 62 picoseconds. So it doesn't matter which way it's biased. If there's 30 picoseconds of skew, this will still be met. Now this guy, we're going to have to extend the period of, mainly because in this scenario, instead of adding the skew to the right-hand side, or to the left-hand side, we're going to add the skew to the right-hand side. And so all that changes is we have an extra 30 picoseconds for our clock period, which is going to be 390 now. And so when we actually calculate our frequency, we should get around about like 2.52, 2.53 gigahertz, something like that. Let me know what you guys get for your calculation when you do 1 over 390. Should be around there in the 2.5 something range. Sounds good to me. at 2.56 gigahertz. Okay, cool. So you'll notice that because of this skew, we've actually decreased our operating speed by 0.22 gigahertz or 220 megahertz. So a significant loss in the number of instructions we can actually, or the number of times we can use the circuit per second. Okay. So we've gone over an example of given some sort of an unknown amount of skew, how much skew we can deal with. We've gone through an example of, okay, we're given a skew. What does that affect in our equations? I think that's about all I wanted to go over. Typically, in the problems, if you're given a skew, if you're given like 30 picoseconds, you likely won't be told where it's biased, and so you have to assume it's the worst case scenario for both. So you'll assume that you add it to the left-hand side for the hold time and add it to the right-hand side for the clock, because you don't know which way it's skewed. So you assume worst case scenario for both. So in this case, worst case scenario for this would be add 30 to the left-hand side, but it'd still be met, because 45 is going to be less than 77. And we already did the calculation for the worst case scenario for the clock time, which would be 2.56 gigahertz. Okay, so now that we've talked about that, anyone have any questions in regards to this process, doing timing analysis?
Just a quick question.
Yep.
If we were just given the timing diagram, so we need to derive all of this stuff for timing. So the first clock will have TPCQ, TPD, TCD, TCCQ, and T setup, while the second clock will have TC and T hold, right?
Yes, that's right.
Okay, thank you.
That was a bit loud. Yeah, that's right. Yeah, the setup time and the hold time are the two times, but is the time before and after the receiving clock. And then all of your TPD, TCD, TPCQ, TCCQ, and all of those are going to be with reference to where your first sending clock is coming from. That's right. Okay. Any other questions in regard to timing analysis? Okay. So we went over timing analysis. We went over synchronous versus asynchronous flip-flops. We talked about implementing higher order 8-to-1 multiplexers, both structurally and behaviorally. I feel like there was something else that I forgot. But those were the topics we covered. Anyone else have any other questions for me?
I'm all good over here.
Okay.
Wait, T setup as the time needed before it enters the second clock, or is that T hold?
Before.
Okay, and T hold
Yeah.
is after it leaves.
Yeah.
Needs to be stable. Okay.
Okay. So I'll take that as everyone is going to get an A+ on the exam.
We will do proud.
I believe in you guys.
Not
You
me.
guys got this. All right.
I feel like we're in a good place.
So let me think. For tomorrow's office hours, I'll still be here. So if you guys have any questions from your exam tomorrow that you want to talk about, let me know. I'll ask Dr. Harris if she cares. I don't think she's gonna care, because I think, does she only have one section for 200 this semester? I think it's just one.
I recall, yeah, when I was registering, there's only one section.
Okay, then I don't think she'll care if I go over homework problems. If there were two sections, I'd be like, oh, well, let me wait. But yeah, tomorrow, office hours, if you have any particular exam questions that you remember and you want to go over, let me know, and I'll go over all of them with you guys. All right, well, good luck, everyone, on your exam tomorrow.
Thanks for helping us.
Yeah, of course, my pleasure.
I think we'll do good.
Yes, I think so too. And I'll see you guys for tomorrow's office hours at 5:30.
Thank you very much.
Thank you, Victor.
Very well.
Thank you.
Yep.
Yeah.